Today I decided to devote the entire day to Gaussian process regression, and there are two reasons. A, I find it interesting myself, it's good enough, but B, it has been invented many times over, which always is an indication that perhaps it is something meaningful or something, something deep. So as far as I know, it started with Volt, but maybe somebody will find that it was known even earlier. So he was a Scandinavian statistician. Then Norbert Wiener, a very famous guy, he invented it in the context of time series. So Norbert Wiener was a famous math prodigy. So he got his PhD at age 17, I think, and later went on to become a very important mathematician. And you see him here pictured on his book called Cybernetics. So he was the founder of this field. Then Kolmogorov. So they pretty much, or they to a large extent, they worked in the same areas. So this is Kolmogorov was the Soviet Wiener. Then there is Kriging. He was a South African mining engineer, and nobody knows how to pronounce him properly. I think Kriging is about right. And the method is also called Kriging, or Kriging, after him. But being a modest guy, he didn't call it that himself. Rather, it was called that way by Materon, who was a very influential figure in France. Georges Materon. He is the godfather both of the French version of geostatistics, but also of mathematical morphology. Mathematical morphology is one particular approach to image processing, and he actually founded an institute, and his intellectual grandchildren are occupying this institute. So people on one floor are working on geostatistics, people on the other floor are working in mathematical morphology. It's in Fontainebleau, close to Paris, and if you get a chance to work with them, this is a good place. So it's been reinvented many times, and it came at least under the following names: best linear unbiased estimation, Kriging, and then when the machine learning people also discovered it, they called it Gaussian process regression. And this is, well, at least in this field, the name that seems to stick. Okay. By the way, why was Kriging relevant to this? He was a mining engineer, and well, drilling holes when you dig for gold or oil is really expensive, so you want to make the best possible use of your experiments. So it really matters to get the modeling right. So Kriging, or Gaussian process regression, I start with a very abstract summary. It's a flexible regression method. And its chief merit, I would say, is that it also gives an uncertainty estimate. So putting an error bar on your numbers should always, be sufficient motivation to you. But this is in particular why this method is of interest for active learning, for example. Now, when I say flexible, this is good and bad. It has many design parameters which are embodied in the covariance function that's being used. You will see in a moment, or in a few moments, what mathematically speaking, so how this covariance function enters. But I want to start with it and its parameters for now. So this covariance function expresses our, or the similarity measure, or the kernel if you wish, expresses our prior assumption about how similarity in of your true response function, how similarity decays with distance. And well, a popular covariance function would look like that. But you can do other things, so you can, another extreme would be this one here. You can, well, there's a whole family, or of functions that you could use here. What matters on the one hand is their range, so how quickly it decays with distance. So, for example, standard deviation could be a measure of the range, provided it exists. Another important measure is the sill. Which I'm going to mention only after the Nugget Effect. So here this reveals its origins in this case, gold mining. Why is this called Nugget Effect? Because it says that at distance 0 you have a high similarity, and then as your distance grows just a tiny little bit, your similarity drops, and then it decays with distance. It comes from gold mining, because on the scale of a gold mine, gold nuggets are infinitely small. So, if you are hitting a gold nugget, and if you stay within, a micrometer or a millimeter, you will find more gold. So we have high similarity. But normally, let's say the gold mine or the field where you're looking for gold, maybe hundreds of meters or even kilometers across, and this is more the scale that we're looking at here. So what this means is that if we tend to find gold here, then we also tend to find gold, let's say, within a 1 kilometer radius. But we have this discontinuity at the origin here. So this is the nugget. And then the overall height of this is called the sill. And of course you can set the nugget to 0 if you like. And now these three functions that I plotted here, they all look pretty similar. They mainly differ in their behavior at the origin here. And what we need to consider here is the degree of differentiability at the origin. So what I mean is the following. Well, distance cannot be negative, so I just plotted 1/2 here of the similarity function. But in one dimension, let's say we want to measure similarity relative to this point here. If I'm taking two of the extremes examples that I've plotted, one was like that. And you see that it's continuous at the origin, but there is a jump in the first derivative. So this is not at all differentiable at the origin. On the other hand, if you use a function that is very smooth, like this one here, so if I take the RBF kernel, for instance, we could say that this is differentiable an infinite number of times. So all derivatives exist. Derivatives of arbitrary order. Whereas this here was an exponential decay. or e to the minus absolute value of x. And here I had e to the minus sorry, I should first close the norm. Square norm of x up to some scaling. So let's, I'm underlining again all the parameters that we have. So as parameters, we have the sill, we have the range, we have the differentiability, we have the nugget, and in addition, if you have multiple dimensions, well, you can have different ranges in the different dimensions. So quite a few parameters here, which means our model will have lots of expressive power, but unfortunately the parameters will also be hard to determine in practice. So in practice it's always the same, and in theory I think you could have it different for the different dimensions. Yeah. Okay, so this is the covariance function or the similarity function that we're going to put in. And in the following few slides, I will assume that somehow you know, we know already which function to use. I will only later talk about how to estimate what would be a good function here. Okay, now today I want to talk about 3 ways that will give us essentially the same method. So perhaps you will find one of these ways more intuitive than another. So it's going to be a very meditative day. Okay, we're doing the same thing thrice. It's going to be our, how do you say, mandala? I'm not so into these things for today. Yeah. So first approach is to use a kernelized view of regression. So if you remember last time when we talked about regression, I used this perhaps a little bit funny notation where y, it's actually a vector, but it's a row vector, and this is why I gave it a big letter. So y is 1 times n, where we have n observations, each of which has p dimensions or p features. Then B transpose was our set of parameters. So B transpose here is 1 times P. And then X is the matrix holding all my original observations. So this is P times N. And then I'm using a large epsilon here for the noise term. Could you please close the window? Thanks. And last time we found that our best estimate for these regression coefficients is given by the following. And that could be used to make predictions. Now, I want to use the kernel trick. And when we talked about the support vector machine, we said that the kernel trick means to replace an inner product xi, xj by a kernel function depending on these 2 parameters. And in fact, we said this could be considered as a shortcut because I could also map the first vector to a high dimension and map the second vector to a high dimension. Take the inner product of these and write that as a kernel. So in the first line here, this would be a linear kernel, and if phi is a nonlinear mapping, then the second line here would be a nonlinear kernel. And we discussed different kernels. We said that there is, for example, the polynomial kernel, or the radial basis function kernel, and a few others. Now, the prerequisite to use the kernel trick is that I must always have pairs of observations. So here, for example, I have an inner product of observations that would work for the kernel trick, but here I have just a single dangling observation. So I want to now go to the dual domain where we can express everything in terms of inner products. So in the dual domain, we can express all computations in terms of inner products between observations. Now, when we talked about support vector machines, we used the following kind of approach, which has been well suggested by different people for kernel regression, but one of them has been Saunders and colleagues, 1998, something called kernelized regression or so, this paper. What you would do is the following. You would minimize, if I talk about kernelized regression, then I can introduce a biasing term, a regularization term that will encourage short parameter vectors. So I'm using some constant, let's say 1 over c times the squared L2 norm of my coefficient vector plus a sum of squared slack variables. In the SVM, these were linear, and here we have a sum of squared slack variables. And the slack variables are given by the following condition, that each observed response yi should be explained by the beta that I found plus the slack. So the slack is my residual. It's essentially what I called epsilon up here. And the task is to minimize this with respect to beta and the slack variables. And I can now build a Lagrangian form of this. So the Lagrangian would have these primal variables as well as my dual variables, the Lagrange multipliers. Here they come. So we have one Lagrange multiplier for each of these constraints. There we go. And now we could proceed as you saw in the SVM lecture, we would want to minimize this with respect to the primal variables and then maximize it with respect to dual variables and so on. And this will work. However, today I want to use a different argument to get to the same solution. It's not any more, it's not more elegant, but I just want to show you a different way of getting there. Namely, so a prediction y hat is going to be given by my estimate times an observation. So this is now a 1 by 1 and wouldn't it be nice if I could express my parameter beta as, let's say, B transpose X transpose X. So this is the matrix that holds all my training observations. That's a capital X, and this small x here, this is my query point, so where I want to make a prediction. Because if I could do it that way, then I would have an inner product here, and I could use the kernel trick. So the question is, can we express our parameter estimate beta hat as our training or design matrix X times some vector B? Question mark. And the claim is yes, this is possible. And I will argue via the SVD. So we're using the singular value decomposition here. So I'm saying, or I'm decomposing my design matrix X into U, S, and V transpose. And I am then rewriting my parameter estimate, which I'm copying down again for your convenience here. I'm now inserting the SVD here. So this gives me V. S is the same as S transpose. Now U transpose U is the identity matrix. And I then obtain V S squared V transpose to the power of -1. And I want to rewrite this. Oh, I had a mistake here. Sorry, this shouldn't be X transpose X, but XX transpose. Okay, using the convention that I have here, and then I have U as V, and then V as U transpose, and that gives me U S squared U transpose. Okay. Okay. Now, in general, I can, so I have a product of 3 matrices which I want to invert, and I can write that as a product of the inverted matrices because of the following relation. So if I have some matrix A and B, I can write that as B minus 1 times A minus 1, and I'm going to check this, that this is true simply by multiplying it out. So AB minus 1 times AB is the identity matrix. And if I'm now using this claim here, I get B minus 1, A minus 1, AB. And you see that these will give the identity matrix, and then those will give the identity matrix. So this statement is correct. So if I'm now applying it to this formula here, I can see that I can bring this U in front and invert it, and the inverse of U transpose is just U. And I bring this one here and invert it, which will give me U transpose at YT. Okay, and if we are squinting and looking at this from a distance, then we see that this entire thing here is a vector, because Y transpose has a dimension of 1, and this has a dimension of R. If my matrix has rank R, and this here was R by R. So I'm finding that this is U times, I'm abbreviating all of this as a vector A. But my original aim was to express beta hat as X times B. But I can show that these are equivalent, because U is a basis for the column space of X. So the column space is the set of all points that can be attained if I take any linear combination of the columns of X. Because I can write U times A so what I do here, if I take this product, is that I take a linear combination of the columns, just by the laws of matrix multiplication. This is a linear combination of the columns of X, whereas that is another linear combination of the columns of U. And I can again use the SVD here. And then I see that this here amounts to the vector A. So overall, I can say that beta hat can be written as X times B. And this was the question that I had asked. So can we express beta hat as X times B? And we start with beta hat, and at the end we find that yes, I can indeed write this as X times B. Okay, so I can now use this way of expressing my coefficient vector to obtain a dual representation. if I summarize this entire page here, what's important is that, in fact, I can write beta hat as x times b. This is the only thing I wanted to show on this entire page here. Now I can use that to express the mean squared error. Which is often abbreviated as MSE. This is a 1 by n vector. This thing here is a n by 1 vector. And I'm now inserting this expression that we've just found. So I'm writing this as y minus b transpose x transpose x. Okay, so this was simply by saying that using my optimum beta I can write it in that form. Okay, now I can compute the derivative of this mean squared error with respect to this newly introduced variable b. The first term does not depend on b at all. The second term will be minus twice y transpose, okay. And the third term will be that's a lot of x's. It looks like a Hagar comic. Okay, and I want to set this mean squared, the derivative of this mean squared error to 0. Okay, and now, lo and behold, we can express everything in terms of kernels. We just have inner products. So I am going to call this here capital K in honor of the kernel matrix that we were talking about so much when we discussed support vector machines. So what I find is that K y transpose equals K K B. And this I can now solve. So my optimal B will be K minus 1 y transpose plus any vector, let me call it B hat 0, which lies in the null space of X or of K. So the following equation holds that that should be 0. So I'm not going to mention this anymore. So the solution that I'm interested in is the following here. Okay, and this now allows to make a prediction using the kernel trick. Yes. I think you're right, Luca. I think you're right, but we're anyway just using this part here. So, we can also forget about this comment. But I'll think about it more. Huh? Okay, so now at last we can make a prediction in the dual. And this is an equation that we're going to stare at for half an hour or so after the break. So my prediction at a single point y hat, or at a single point x, so I'm inserting this expression here for beta hat transpose. And because I used capital K for a product of these design matrices, I'm using a small k this time for a product of my design matrix and an arbitrary observation here. And now I'm using the result from here to write this as y times k minus 1 times k. Okay, and now there are different ways of interpreting this equation here. And we will look at these interpretations in terms of pictures and formulas after the first break.